All right, so we're going to talk about how to calculate pHs of bases in this video. We're not going to have to deal with the diluted bases like we did diluted acids in the previous video. We're just going to focus on strong bases and weak bases. So with strong bases, they are like strong acids in that they completely dissociate. So the only substances present once a base is in solution would be the metal that was a part of the salt containing the hydroxide and then the hydroxide ions themselves. All of the base that is soluble will dissociate. So the hydroxide source will be the source of the base, but we do have to account for how many hydroxide ions are present in that salt. The hydrogen concentration will be calculated just like it was with pH for hydroxide, taking Kw and dividing it by your hydroxide amount. For a strong base, this should be quite small. Weak bases, however, do not completely dissociate, so their parent base, their weak base, is going to stay intact. That weak base is going to typically come from ammonia or some sort of organic compound containing an NH group, an amine, along with water. So to determine the hydroxide concentration, we're going to have to use our Kb expression to determine what fraction of that weak base dissociated. And then once we have that hydroxide concentration, we can use it to calculate the hydronium concentration. And again, the relationship between hydroxide and hydronium is seesaw. One's higher, the other's lower, vice versa. So in this one, we want to calculate the pH of 0.75 molar strontium hydroxide. If I recognize this as a strong base, I know it's going to completely separate into its parent ions, strontium ions and hydroxide ions, and that in a balanced equation that would show up as 2 hydroxide ions are formed for every 1 strontium hydroxide molecule that is dissociated. Because of that, the hydroxide concentration is not 0.75, but double that, 1.5 molar. There's 2 OHs for every 1 SrOH2. When I calculate the pOH with that information, I get that the pOH is actually negative 0.18. Remember we said that any sort of hydroxide concentration or hydrogen concentration greater than 1 is going to result in values that fall outside of the 0 to 14 pH scale that we're more comfortable with. So this is not surprising. Now that we have our pOH, we can use it to calculate our pH, and we get that to be 14.18. We're going to work backwards this time. We want to know the concentration of an NaOH solution that has a pH of 10.5. So NaOH will dissociate as a strong base into its parent ions, sodium ions and hydroxide ions. 1-to-1 ratio this time, so that's going to help us some. We know that strong bases completely dissociate, so those are the only ions present in our solution. All of the sodium hydroxide has dissociated into hydroxide. So if I know my pH, I can use that to find my pOH, which would give me a value of 3.5. I can use that pOH value to calculate the hydroxide concentration, 3.2 times 10 to the negative fourth. And because there is only one hydroxide ion in sodium hydroxide, that is also the concentration of my NaOH solution. For weak bases, again, you would have to be given Kb values or it would have to be present on your table. Here we have hydrazine N2H4 that's being added to water. When you have a base, again, it's going to accept protons. So the base is taking a proton from water, which is why H2N and H2 turned into H2N and H3 plus, and then OH minus is left behind. We want to calculate the pH of 2 molar hydrazine in water. So just like with the weak acids, we know that the weak base and water are going to be the primary species present in our mixture, and that if we set up our Kb expression for the dissociation of this base, we should be able to determine what fraction of H2N and H2 was able to generate hydroxide ions using my value for Kb, 3 times 10 to the negative 6. Again, hopefully you're going to get to a point where you don't need to use the ice charts for problems like these because you're going to see them set up in a similar manner each time. We know the initial concentration of our base. We don't have any of its conjugate acid or of the hydroxide ions. reactants have to go down, the products have to go up. But if we look at that K value compared to our initial concentration of our weak base, it is ridiculously larger than that Kb value. So we're going to make the assumption that that X is going to cause a negligible change in the concentration of hydrazine. When I do my calculation, I get that the X is 0.0024. If I test this out using my 5% rule, I see that it truly did meet that criteria. It is 0.12% of that initial concentration. So now that I have what X is, I have what hydroxide is. I can use that hydroxide concentration to calculate my POH, 2.62. But I didn't want to find POH, I wanted to find pH. And we know bases should have pHs above 7, in theory up to 14, as long as they're not super concentrated. So I have to do that 14 minus the POH to get the actual pH of my solution, 11.38.